Hi, my name is Terry. This is part 2 of the video I began a little bit ago, double integrals over general regions. I did one example in the last video and I'd like to extend that and do a second example in this video. So this is part 2 of, just so I can do example 2 here for you. Just to recap quickly, to set up double integral over a general region, we have type 1 and type 2 of two ways to do this, because you're dealing with a surface with in multivariate with two variables. So when we're integrating and setting up double integrals, we're going to either integrate the y first then the x, or the x first then the y, so that indicating there is two ways you can set up the double integrals. Okay, so using the vertical slices if you're going to do the y then the x, or the horizontal slices if you're going to just do integrate the x first then the y. So explain this a little bit more in the part 1 of this series here. So we're going to move on to example 2. All right, so example 2 is written here on the board. So we want the double integral over our bounded region D of y dA. Okay, so this is what our double integral integrand is, okay? Where your boundary is going to be a triangle. It's going to be a triangle, and the vertices of the triangle are given, all right? So let's go ahead and set up, let's draw the boundary and set up a type 1 first. Okay, so we're going to do type 1 first. So the boundary is a triangle. Here's the x-axis, here's the y-axis, all right? The vertices of the triangle are the origin, so 0, 0, 1, 1, okay, I'll draw that about here, all right? So 1, 1, and then 4 on the x-axis, so out to 4, 0, okay? So these are the boundaries. This is my base right here, all right? So here is my base. So what I need to do first, so I need to go ahead and I need to write equations for the line segments that form my triangle. I need to write equations of the three sides of the triangle. So let's start doing that. Well, the base of the triangle right here is the x-axis. So written in equation form, we could call this y equals 0. All right. Right here you have, because 0, 0, 1, 1, if you computed the slope, the y-intercept, you could probably reason through here that this is the equation y equals x for this side here, okay? Now, what about this side over here? Well, let me do a little bit of work to get the equation of this line, all right? So to write the equation of this line segment, I need to know what the slope is. All right, so I'm going to compute the slopes, so I'm going to erase this when I'm done. I'm just going to do a little bit of work to get the equation of this line. So my slope, subtract the y coordinates in the numerator, subtract the x coordinates in the denominator, so you end up with 1 over negative 3. My slope is at negative 1/3. All right, and then let me take one of the points on this line segment. I'll take the 4, 0. All right, my slope is at negative 1/3. All right, so write the equation of the line. So y minus your y coordinate, negative 1/3 quantity x minus your x coordinate. So the equation of this line is going to be y equals negative 1/3 x, and then negative times negative is 4/3. Okay, so just writing the equations of your boundary. So this boundary here, I'm going to call it 4/3 minus 1/3 x. Okay, so here are the boundaries. So first thing you have to do when you're given triangular base, parallelogram base, when you're given bases that have line segments, you're going to have to take the vertices, find slopes, y-intercepts, and write the equations of linear equations for each of the boundaries. Okay, so here's the work. I'm going to need the space to work out the Calc 3, the double integral, but all right. So here's what you had to do to get the boundaries here, okay? So now we're going to go ahead and set up a double integral to evaluate the volume of this surface, okay, to this triangular region, all right? But to do that, something happens here with the type 1, okay? So type 1 are your vertical slices. They are your vertical slices. So if you put a vertical slice here, okay, can you see right here, your vertical slice is going from y equals 0 to y equals x right here, okay? However, if I put my vertical slice over at this end, my vertical slice is going from y equals 0 to y equals 4/3 minus 1/3 x, okay? So if you want to use a double integral to find your volume of the surface, okay, you're going to have to, for this type 1, you're going to have to set up 2 sets of double integrals and add them together, because right here, okay, right here, your top curve, if you will, okay, your top linear segment switches on us, okay? So we'd have to set up a double integral to take care of this piece right here, okay, from 0 to x. We would have to set up a second set of double integrals to take care of this piece over here, from 0 to the 4/3 minus 1/3 x. And then we would have to take those 2 sets of double integrals, add them together to get your total answer. So doing a type 1 for this problem is pretty involved, okay? So let's go ahead and set it up. So your type 1 for this, you're going to set up a double integral. All right, so let's start with this piece over here. The integrand is y, okay? So we want to use dy, okay? So it's a type 1, so dy means you're going to go, now we're using this piece over here, this side of it goes from 0 to x. So your lower bound is 0, your upper bound is x for this slice, for the vertical slice, okay? Now, what about the outside bounds, okay? So what about your dx bounds? Well, your dx bounds are going to go from, you got to go from the x to the x to handle this piece here. So your outside bounds are going to go from 0 to 1. All right, so here's your first piece, okay? But that only takes care of the origin to my green line here, all right? So now what about the rest of your solid, okay? So the rest of the solid, we're gonna have to set up another double integral. All right, so we're gonna have to set up another one to take care of this piece, okay? So, all right, so dy, so your vertical slice here, okay, your vertical slice here goes from 0 to the 4/3 minus 1/3 x. It goes from 0 to the 4/3 minus 1/3 x, okay? And then your outside bounds, okay, your outside bounds, the horizontal in terms of dx, okay, your x bounds, your horizontal bounds, okay, go from 1 to 4. Okay, so these outside bounds go from 1 to 4, all right? So we need 2 sets of double integrals to take care of a type 1 for this example, 2 sets of double integrals, right? Because when you use vertical slices, your top-bottom curves switch on you at that point of intersection, all right? So you're going to have to go from 0 to x, from 0 to 1. You have to go from 0 to 4/3 minus 1/3 x, from 1 to 4. So that's how you'd have to set these up, all right? And now let's do the integration. Both integrals, we're going to integrate with respect to y first, okay? So integrate with respect to y first. So you have the 0 to 1, we'll hang on to that. All right, integrate with respect to y, so you're going to have y squared over 2, okay? And this gets evaluated from 0 to x. All right, and then we'll take care of the x afterwards, all right? And then integrate with respect to y, so this gives you y squared over 2 again, all right? All right, but these bounds go from 0 to 4/3 minus 1/3 x, and then we'll integrate that with respect to x, okay? Plug in the upper bound, lower bound here, fundamental theorem of calculus over here is going to give us, let's see, so we're going to integrate from 0 to 1, we're done with this. Plug in the upper bound, x squared over 2, okay? Plug in the lower bound, gives us 0. All right, so we've evaluated this, okay? Let's go ahead and evaluate this one here. All right, so we'll integrate from 1 to 4 and we're done. Plug in the upper bound, gives us 4/3 minus 1/3 x, quantity squared, because we're plugging this expression in for y, over 2, okay? Plug in the lower bound and you're going to get 0. All right, so when you plug in the upper bound for y, you plug in the expression for y, you're going to have this quantity squared over 2. When you plug in the lower bound, you have 0. All right, now we need to integrate both of these integrands with respect to x. So let's integrate this with respect to x. Integrate with respect to x, you get x to the 3rd over, there's 2 already there, multiplied by 3, 6. This gets evaluated from 0 to 1, all right? And then over here, let's simplify this a little bit. I'm going to pull the 1/2 out. We're going to integrate from 1 to 4 of the 4/3, okay, minus 1/3 x, okay, quantity squared. We want to integrate this, all right? I'm going to use a u substitution on this one. I'm going to let u equal the inner part 4/3 minus 1/3 x, inner part of the composite function. So my du is going to be a negative 1/3 dx, okay? So essentially I'm pulling out a negative 3, I'm going to integrate the u squared, okay? So let me work through. So plug in the upper bound, lower bound here. This over here is going to give me 1/6. All right, so whatever I get from this integral here, I'll have to add my 1/6 plus 0 onto that, okay? Over here, so I'm going to do the integration. So when I do the integration here, I'm going to pull out the -3, okay? When I integrate my u squared, I'm going to get this quantity cubed over 3, okay? So I'm going to get this quantity. All right, so this is going to be multiplied by, okay, this quantity here, 4/3 minus 1/3 x, okay, and this quantity is going to be cubed, and I'm going to put that over 3. When I do the integration, this gets evaluated from 1 to 4, okay? So I have my 1/6 here, okay, and I'm going to add to that, well, let's go ahead and evaluate this, all right? I'm going to move the 3's out of the way, okay, so I'm going to move the 3's out of the way, okay? All right, so this gives me bring the negative out, so it gives me a -1/2 out front, so -1/2. All right, so bringing the negative out and moving the 3's out of the way, all right? So now let me just use the fundamental theorem of calculus, plug in the upper bound here. So when I plug in the upper bound, okay, plug in 4/3 minus 4/3 is 0, okay? So 0 raised to the 3rd power is 0. All right, and then when I plug in my lower bound, okay, so plug in my lower bound, I have 4/3 minus 1/3, that's 3/3. 3/3 to the 3rd power is 1, so that's 1 for this, okay? So I have 1/6, and I'm going to add to that, I'm plugging in with my expression here, all right? So I'm going to take my 1/6, and I'm going to add to that my, what do I have here? 3/6. All right, so it's a -1/2 minus, so I have a negative here, and so that gives me 4/6. Okay, which reduces to 2/3. All right, so my answer is 2/3. Just working the computation here. So 1/6 minus, so -1/2 times a -1 is a +1/2. So 1/2 is 3/6. 3/6 plus 1/6. We have 4/6 for an answer, so 2/3. 2/3 is the answer. Now we had to set up 2 sets of double integrals because of the way this region has worked out. Okay, let's go ahead and take a look at the type 2. All right, so let's go ahead and take a look at the type 2. All right, and see how this is gonna be for us. Okay, so let's take a look at a type 2 solution for the same region, for the same boundary, type 2 solution. Okay, so the type 2 solution, we have the same boundary, don't we? Same boundary. Okay, so you have the x-axis, you have the y-axis. All right, we have the origin here. Okay, and then we have 1, 1 and 4, 0. So y equals x over here. Well, I'm going to call it x equals y. Okay, that's this side. All right. And then the equation on of the line over here, that equation was y equals, we had 4/3 minus 1/3 x. Okay. So y equals 4/3 minus 1/3 x. Well, let's change this to x equals because we want to do it type 2, which means we're going to use horizontal slices for this one. Okay. Horizontal slices means we're going to integrate the x first, then the y. To integrate the x first, we have to write the inside bounds as a function of y. So I need to know what x is in terms of y. So let me subtract 4/3 from both sides. Okay, so y minus 4/3 gives me a -1/3 x. And then I'm going to multiply every single term by a -3, so that gives me -3y. Okay, multiplied by a -3, the -3 cancels, plus 4 equals the -3's cancel. So x is going to be 4 minus 3y. So this line over here is going to be x equals 4 minus 3y. Okay, so the equation of this line right here, written y equals in terms of x, it's 4/3 minus 1/3 x, but when you solve for x equals in terms of y, 4 minus 3y. All right, so let's go ahead, we're going to set up a type 2 integral. Okay, so the type 2 integral, here's your double integral, the integrand is y. Okay, so the integrand hasn't changed, it's y. Now we want to solve, but we want dx dy here, dx for the inside bounds. So dx for the inside bounds means your inside bounds have to be x equals as a function of y. X equals is a function of y. And so if you notice here, we don't need two sets of double integrals here because the entire region, you are going from this segment to this segment covers the whole region. So what are the x equal bounds in terms of y? Left to right, you're going from y, okay, to 4 minus 3y. All right, so those are the inside bounds right there. Now what about the outside bounds? Okay, the outside bounds, the dy, the outside bounds. Well, dy means we want the vertical representation of the bounds, okay? So where are the y's going? The y's, the vertical representation, the y's are going from 0 to 1, so 0 to 1 for the outside bounds, okay? Here's how you would write it, type 2. So type 2 is easier than type 1 in this case. Type 1, we had to set up two sets of double integrals to achieve our answer. Type 2, this is easier. This is one set of double integrals, and let's see how this goes. So let's go through, we're going to integrate y with respect to x, okay? So 0 to 1 for the outside bounds. With respect to x, that means y is constant. When you integrate y with respect to x, you're going to have x times y. All right, we're going to evaluate this from y to 4 minus 3y, all right, and then we will integrate with respect to y in a brief minute here, okay? Fundamental theorem in calculus, okay, so fundamental theorem in calculus, we're going to plug in the upper bound. We integrated with respect to x. X is the variable, so the substitutions get made for x, okay? So you're going to have 4 minus 3y being multiplied by the y. Plug in the upper bound, and then when you plug in the lower bound, gives you y times y. So that's going to be y squared, and we're going to integrate this with respect to y, okay? Let me go ahead and we'll evaluate from 0 to 1. Let me go ahead and simplify in here. So we have 4y minus 3y squared and minus another y squared. So I'm going to write minus 4y squared when we simplify the integrand, okay? So we have 4y and then minus 3y squared, subtract another y squared, so 3y squared minus another y squared is 4y squared, okay? Integrate each with respect to y, so 4y squared over 2 gives us 2y squared for the first term, 4y to the third over 3 for the second term, and we're going to evaluate this from 0 to 1. Plug in the upper bound gives us 2 minus 4 thirds, okay? Plug in the lower bound gives us 0 minus 0, so 2 minus 4 thirds, that would be what, 6 thirds minus 4 thirds, and 6 thirds minus 4 thirds is 2 thirds, okay? So 2 thirds for the answer. So this example, I think you can pretty clearly see that type 2 would be your easier solution. They both work, but you know, type 2, easier solution because you only had to set up one set of doubles. You're just going from this, across the region, you're going from this line segment to this line segment, no matter where you decide to place your horizontal slice, okay? Whereas the type 1 solution, you would have to set up two sets of doubles because of vertical slices here. When you set up your vertical slices, okay, or on this side, you're going from 0 to x, but this side, you go from 0 to the other line segment. It splits up on you, which means you're going to have to do these pieces separate, add them together, okay? All right, so this is a little bit more involved example. Hope this helps. Thank you for watching, and that concludes this video. All right, and stay tuned. I'm going to make a few more videos, so stay safe out there, stay healthy, and thank you again.